We're going to talk about the first law of thermodynamics and ways to add energy to a system. Those two ways are working and heating. So doing work on a system and then also heating up the system by transferring energy into or out of the system via heating. So energy transfers out of a system and into its surroundings when we're doing work, when the system is expanding. So the system pushes on the surroundings, and you can think about the system doing positive work on the surroundings. So your system is pushing the surroundings to the right, the surroundings are moving to the right, so the system does positive work on the surroundings. You can also think of it as the surroundings doing negative work on the system. The surroundings push to the left on the gas, but the gas moves to the right, the system moves to the right, so we know work is FD cosine theta. Theta is 180 degrees, and cosine of 180 degrees is -1. So we know that we have negative work done on the system. You can also think about the fact that since the system is doing work on the surroundings, the system must be losing energy because it is giving some of the energy to the surroundings. Since it's doing work on the surroundings, it must be transferring energy out of the system into the surroundings. So when the volume increases, the work done on the system is going to be negative. Then we can think about energy transfer out of the surroundings and into the system. For this situation, the piston would move to the left, so the gas inside the system, which is the gas inside the cylinder here, would be pushed to the left and it would move to the left. So that's positive work done on the system. The surroundings are doing work on the system. They're pushing it to the right. They're adding energy to the system. So positive work is done on the system when the volume decreases. Another way to change the energy of a system is by heating it. And we can heat it by conduction is usually the way that we heat it. It could be radiation as well, especially for the cooling process, that could be radiation. But when we transfer energy from the system to the outside, so if the system and the surroundings have different temperatures, we know that they're going to gain equilibrium eventually if we just let them sit, right? And so the energy is going to transfer from the hot to the cold. And so heat's going to transfer out of your system if your system is hotter than your surroundings. But if your surroundings are hotter than your system, then heat can transfer into the system. If you have an isolated system, you may not have much heat transferring, but you will have heat transferring if there's a temperature difference between the surroundings and the system. So we are going to do a little simulation so that you can see some things about heat transfer. It's really important to know that heat always flows from hot temperature to cold temperature. And let me pull up the simulation real fast. Okay, so I'm going to add 100 particles on the left side and 100 particles on the right side. Oops. I'm going to make the left side, since it's blue, we'll make it cold, 50 degrees Kelvin, and the right side will make 500 degrees Kelvin. So you can see that the right side, the particles are moving faster because they have more internal energy, shown by their temperature being warmer. On the left side, we have the particles moving more slowly because they are colder and they have less internal energy. But right now, there's a barrier in between them. So there could be an energy transfer through a barrier, like if this barrier were the wall of your house, and this is the heat inside when it's cold outside, and this is the cold air outside. These air particles, these hot air particles, will collide with your wall and speed them up a little bit, heat them up a little bit. Those wall particles in the surface of your wall will heat up the next ones and the next ones and so on until they get all the way through the outside wall. So now the outside wall is a little bit warmer, and so when the air particles here, the cold air particles, hit your wall, your outside of your house, then they are going to be sped up a little bit because some of the energy will transfer from those fast-moving particles to the cold-moving particles. Now, this is all completely random motion. Also, it's important to note that the collisions between the particles, when we are assuming that it's an ideal gas, we're assuming that the collisions are elastic collisions. So kinetic energy is conserved in the collisions and momentum is conserved in the collisions. For all collisions, we know momentum is conserved, but for kinetic energy, kinetic energy conservation that only occurs for perfectly elastic collisions. And that's what we're assuming. These are little gas particles that are moving around quickly. They have collisions with other ones, but really it's their like electron clouds are repelling each other when they come close, and they bounce off like that. So it's not like their nuclei are smashing into each other and dissipating a bunch of energy. So they're they're pretty much perfectly elastic collisions. Now I want you to watch what happens when I remove the divider. When I remove the divider, we're going to have an interaction of the hotter particles and the colder particles. And when the warmer particles run into the colder particles will speed up, the original blue ones, and the warmer particles, those red ones, those are going to slow down. So the energy is transferring. The red particles have more energy than the blue particles, and the energy is slowly transferring to those blue particles. I also did not show this, and I'm not really sure. Usually it showed me the changing temperature, but let me, data? Yes, here we go. So, so we can see that this is the blue over here. So it started off at 50. The red particles started off at 500, and so now they're getting closer and closer to the same temperature. So if we let this go long enough, they will transfer the red will transfer enough energy to the blue that they effectively have the same energy. Now notice that not every particle has the same energy. There's a range of speeds, but the average energy that they have tells you the temperature. Okay, let's go back to our presentation here. Okay, so here's our first law of thermodynamics, and that is that the internal energy in a system plus all of the energy changes in a process is equal to the final energy, and that shouldn't be a surprise to you. So we have internal energy plus work, and that's work done on the system, not work done by the system, plus the heat. And heat will be positive if energy is added to the system, and Q will be negative if heat is taken away from the system. So heat exits the system. That equals your final internal energy. So then we can subtract our internal energy over here, and we get, this is the one that you'll see on your AP equation sheet, change in internal energy, and U stands for internal energy. This one is dependent on temperature, and you can find that by using the equation 3/2 nRT, or 3/2 capital M, which is number of particles, times K, which is Boltzmann's constant, times T. That's equal to the work done on the system plus the heat, which could be added to or subtracted from. Also, remember our work could be negative, so if the system is having energy added to it, so the surroundings are doing work on the system, then work will be positive. If energy is leaving the system and the system is doing work on the surroundings, then your work will be negative. We can also draw some bar graphs and flow diagrams. So this is just like our conservation of energy study where we had an initial amount of energy, but here we're showing internal energy. And we, like I said, we can calculate that using this equation. Then we have our system flow diagram, and your system flow diagram is here. So you will show your work and your heat on the system flow diagram. So if heat is being added to the system, you would show the arrow pointing in. And if heat is subtracted from the system, you will show the arrow pointing out. Same for work. If work is being done on the system, you will have your arrow pointing in with your number of blocks. And then if negative work is being done on the system, so energy is leaving, you will have your arrow pointed out and you will have your number of blocks there. When you add those together, your Q and your W, you will get a final amount of internal energy. And you'll be able to calculate it here and then also draw a representation on an L diagram. And aren't you excited to do LOL diagrams again? I know you are. That's the end.